This is part 3 to the chapter 5 videos, and in this video I'll cover differentiation and integration with the natural log function. So I wrote down the derivative of the natural log of u is 1 over u times u prime. That's just regular chain rule, where u is a function of x. And when you integrate 1 over u du, you get the natural log of the absolute value of u plus c. So I'll do these 4 examples where you find the derivative, and then these 4 examples where I'll integrate. So the first example is f of x equaling natural log of 3x. So the derivative examples first. All right, and the derivative rule. And so this case, u is what's inside of the natural log, the 3x. So u is 3x. That means u prime, derivative of 3x is 3, because that's derivative of x is 1, so it's 3 times 1. So f prime of x, that's 1 over u, well, u is 3x, so it's 1 over 3x times u prime, and u prime is 3. And then the 3's divide out, so you just get f prime of x equal to 1 over x. And that's it for this one. All right, so I said the 3's divide each other out. Number 2, y equals the natural log of x squared plus 3. So this case, u is the x squared plus 3. So u prime, derivative of x squared, that's going to be 2x, and then 3 goes away because that's a constant, so u prime is 2x. So we know the general rule, when you take natural log of derivative of natural log of u, that's 1 over u times u prime. So for this case, it would be y prime is equal to 1 over x squared plus 3. And then times u prime, which is 2x. So our answer, y prime, is 2x over x squared plus 3. Okay, and number 3, g of t is equal to the natural log of t plus 1 squared. All right, so the notation here is a little confusing because you have this square and it's not squaring the natural log. You could write it as the following. So natural log, and then in brackets have t plus 1 squared. So that's the natural logs applying to that whole thing, including the exponent too. Now there's 2 ways we can do this. We could either just let u be t plus 1 squared. So I'll do 2 ways. So method 1, I'm just going to automatically let u be the t plus 1 squared. So by chain rule, you drop down the exponent, so it's 2 times t plus 1 to the 2 minus 1 times the derivative of t plus 1. Well, the derivative of t plus 1 is 1, because the derivative of t is 1. So u prime is 2 times t plus 1. And then our u is t squared, or t plus 1 squared, and that's our u prime. So g prime of t, so it becomes 1 over u, so that's 1 over t plus 1 squared, times u prime, which is 2 times t plus 1. I could cancel out t plus 1 from t plus 1 squared, so then I just have 2 over t plus 1. All right, and that's going to be the answer. That's directly jumping into using that derivative rule. Just letting u be that t plus 1 squared thing, and I would rewrite it so that it's more obvious that the natural log's applying to the whole thing of t plus 1 squared, whereas it's not doing the natural log of t plus 1 and then squaring it. Method 2 would be using natural log rule. So you use the log rule where it's if you have the natural log of a to the b, that turns into b times natural log of a. So you just bring the exponent in front of the logarithm. So that's one of our logarithm rules. So for g of t, which is t plus 1 squared, or natural log of t plus 1 squared, you could bring the exponent in front of the logarithm, so that g of t is 2 times the natural log of t plus 1. In this case, our u is the t plus 1. So derivative of u, so u prime is 1. So g prime of t, so you factor the 2 out and then focus on taking the derivative of the natural log of t plus 1. Well, that's going to be 1 over t plus 1 times 1. So the same answer, 2 over t plus 1. All right, and that is up to you which way you want to do it. Personally, I would have done it the second way, just because I remember my natural log rules. But you could still do it the first way. It's just you have to use chain rule when you're taking the derivative of t plus 1 squared, which is the general power rule. All right, so the next one's number 4, and it looks sort of complicated. So doing the natural log of x times the square root of x squared minus 1. And I'm going to use some logarithm rules to rewrite it first. So I'll rewrite using logarithm rules. So inside of the logarithm, I have x times the square root of x squared minus 1. So I have a product. So one of the rules I'm going to use is that when you have natural log of a times b, that splits up to be the natural log of a plus the natural log of b. Now you could write the square root as raising to the 1/2. So I could write this as the natural log of x times and then the x squared minus 1 raised to the 1/2. So the point is I have an exponent of 1/2. So I'll use the rule that I used in the previous example. If I have natural log of a to the b, then that turns into b natural log of a. All right, so I can break this up first. Since it's a product, I can break it up as the natural log of x plus the natural log of x squared minus 1 to the 1/2. Then I can bring the 1/2 in front of the natural log for the second one. So this is f of x is equal to natural log of x plus 1/2 times the natural log of x squared minus 1. And now I'm going to find the derivative. Now, if you take the derivative of ln x, that just becomes 1 over x, because the derivative of x is 1, so that'd be 1 over x times 1, which is 1 over x. So anytime it's just x, it becomes 1 over x. So at least I know for this part, that's 1 over x. So f prime of x, so I'll bring it down here. So derivative of natural log of x is 1 over x. And then I'm going to take the derivative of the second term, but first I'll bring the 1/2 in front and focus on taking the derivative of the natural log of x squared minus 1. All right, in this case, u is the x squared minus 1. So u prime, derivative of x squared minus 1, derivative of x squared is 2x. And then the minus 1 goes away because that's a constant. All right, so u prime is 2x. So this turns into, so we have f prime of x equal to 1 over x plus 1/2 times 1 over x squared, that's our 1 over u, or x squared minus 1, 1 over u times u prime. Well, u prime is 2x. And then I can cancel out the 2's. So I have x over x squared minus 1. And then I would be fine with that as the answer. You could try to combine it into one fraction. Let me see if the textbook does that. Sometimes their textbook's a little inconsistent. They'll leave it like how I have it now, or sometimes they might just go ahead and make it one fraction. So let me look at what they have. Yeah, the textbook goes ahead and writes it as one fraction. So for the one fraction for the textbook answer, they get 2x squared minus 1 up top divided by x times x squared minus 1. All right, and that's because they use the x times x squared minus 1 as the common denominator, and they changed both fractions so that it reflects that new denominator. All right, so I'll leave that up to you to get that part as far as rewriting that to that textbook answer if you wanted to do that. But for our purposes, I'm fine with the just 1 over x plus x over x squared minus 1. All right, so first I rewrote the problem using logarithm rules, and I had the 2 logarithm rules for if you have a product inside the logarithm, you can write that as 2 logarithms with the sum. And then I use the other logarithm rule. If you have something raised to an exponent, you can put the exponent in front of the logarithm. All right, so first I recognize, well, I have a product. So I changed it from 1 logarithm to 2 logarithms separated with an addition sign. And then the second logarithm, I put the 1/2 in front of the logarithm. And then I went ahead and found the derivative just using the logarithm derivative rule. And the first one's easy because it's natural log of x. And so that just turns into 1 over x. The second one, taking the derivative of x, natural log of x squared minus 1, u is x squared minus 1. So u prime, derivative of x squared minus 1 is 2x. So that's why it turns into 1 over x squared minus 1 times 2x. Okay, so that's that one. Now I'm going to go into integrals. All right, so these are the integration examples, and I'm using the rule that's in yellow, 1 over u du equals the natural log of the absolute value of u plus c. So number 5, what I would do is factor out the 5 in front of the integral. So we have 5 times natural log of 1 over x dx. Well, based on this relationship, u is x, so this becomes 5 times the natural log of the absolute value of x plus c. Right, just because that's a variable change, just x in the place for u. Now, this is an answer, but you could write this as the natural log of the absolute value of x to the 5th power plus c because of our logarithm rules. And I believe that's, now the textbook just uses this one, but I'm just saying you could rewrite it by using that rule with logarithms, just bring in the number into the logarithm so it turns into its exponent. Okay, so either of those two. And I'm fine with either answer. Number 6 is 1 over 2x plus 5 dx. All right, so this is one where I will have to use some kind of substitution. And generally it's whatever's on the denominator is what u is going to be. So u is 1 over 2x plus 5. And I want to use the relationship that when you integrate 1 over u du, that turns into the natural log of the absolute value of u plus c. Taking the derivative, so we have du is equal to, and then derivative of 2x plus 5 becomes just 2 because it would be 2 times 1 plus 0 because the derivative of x is 1 and the 5 goes away because it's a constant. So it just turns into 2. And then I got to attach my dx. Now notice I have just dx in the integral. So I'm going to multiply both sides by 1/2 to get rid of the 2. So I have 1/2 du is equal to dx. All right, so that's what I'll substitute in for dx. And then substituting u in for the 2x plus 5. So that's going to be 1 over u, and then dx is 1/2 du. All right, so that's the substitution. I'll factor out the 1/2. So I just have it as 1 over u du, and then I just use my rule. That turns into the natural log of u, but I'll just have 1/2 in front. So 1/2 times the natural log of the absolute value of u plus c. I gotta make sure to back substitute. Because u is 2x plus 5. So this would be 1/2 times the natural log of the absolute value of 2x plus 5, and then plus c. Or you could rewrite it, because we know raising something to the 1/2, so using logarithm rules, you could write this first as the natural log of, and then 2x plus 5 raised to the 1/2. And then raising something to the 1/2 is the square root. So this would be natural log of the absolute value of the square root of 2x plus 5. So either one, just mentioning if you use logarithm rules, that's what it would turn into. And then number 7 is x over x squared minus 3. All right, so for this one, and the common pattern here is I've been letting u be what's in the denominator, so that's what I'm going to do here. And I'll use different colors, so I'll let u be the x squared minus 3. That means du. So the derivative of x squared is 2x, and then the 3 goes away because that's a constant. So I have 2x, and then I latch on the dx. Now notice in the integral, I have x dx. I don't have this 2. So I'd multiply both sides by 1/2. So I have 1/2 du is equal to x dx. All right, because that's what I have here. All right, so doing the substitution, I have x dx, that's 1/2 du. And on the bottom is going to be u, because that's x squared minus 3. I would factor out the 1/2. And it is du over u, but I've usually been writing it as 1 over u du. So I'm just going to go ahead and write it again as 1 over u du, because that's just what we've been looking at. And then that turns into the natural log of the absolute value of u. And then I back substitute. U is x squared minus 3. Okay, so that's what we'll get for the answer. And like in the previous one where I had 1/2, you could write it as the natural log of the absolute value of the square root of x squared minus 3 plus c. Technically, since you're taking the square root is going to result in a positive number. So you really could ignore the absolute value sign and just write it as the natural log of the square root of x squared minus 3. Since the square rooting gives you a positive number anyways, the absolute value sort of becomes, I mean, it's not incorrect to write it like that. It's just redundant. Same thing for this. I could write it as just natural log of the square root of 2x plus 5, ignoring the square root, or ignoring the absolute value, because again, it's just redundant. But it is not incorrect to keep the absolute value signs. I just generally just keep the absolute value signs just to be extra careful. So either one of those is the answer. All right, and now the last one for this video, which looks a lot more complicated than what it is. All right, so I claim it looks more complicated than what it is. And why it does is, so we have a bunch of terms here. It's a polynomial over a polynomial, just kind of looks crazy, but I can make it easier. And generally I've been letting whatever's on the bottom be u. So if I let u be the x cubed plus 3x squared plus 9x, taking the derivative, so du, that becomes x cubed's derivative is 3x squared, and then plus 3 times the derivative of x squared, which is 2x, and then plus 9 times 1, because the derivative of x is 1. So du is equal to 3x squared plus 6x plus 9. And then I still have the dx that I attach onto that. Now that's not exactly what I have in the integral, because I have x squared plus 2x plus 3. But for 3x squared and 6x plus 9, I could factor out a 3. And if I factor out a 3, that will give me x squared plus 2x plus 3, and then dx. And that's what I have in the integral, the x squared plus 2x plus 3. It's just I have this multiple of 3. So I got to get rid of that by multiplying both sides by a third. You have 1/3 du. And then the 3 goes away, so now I do have the x squared plus 2x plus 3, and then dx. And I put it all in parentheses. The dx is applying to that entire expression. So this is what we have here. All right, that's my 1/3 du. And everything on the bottom is u. So now I can make the substitution. All right, so what I circled in green down at the bottom, that's the same thing as the x squared plus 2x plus 3 dx. So it's 1/3 du. I'm going to zoom in so it makes my handwriting look better. So I have 1/3 du. And it's all over u because I let the entire denominator be u. And I'll factor out the 1/3. And then I'll have du over u is the same thing as just 1 over u du. And then I use my natural log integration rule. All right, and then I back substitute. Well, u was this entire thing, x cubed plus 3x squared plus 9x. So this will be equal to 1/3 times the natural log of the absolute value of x cubed plus 3x squared plus 9x. And then plus c. And then that's it. That's my answer. All right, so it looks more complicated, at least I think so. It looks more complicated than what it was as far as the work involved. I just rewrote it into that. The substitution makes it a lot easier to look at. So you have 1/3 du over u, which we factored out 1/3, and then we integrated. And the general pattern is I'm letting whatever's on the bottom be u, and then take its derivative. And then I noticed that 3x squared plus 6x plus 9 is a multiple of x squared plus 2x plus 3 because it's a multiple of 3. All right, so that's it for this video. This video covered derivatives and integrating involving the natural log. I'll go into more examples in the next video.